In this last video, we're going to put everything together and do a learning check, and you'll be able to practice everything from this module. So here's our learning check. We have a sample of 16 individuals that are selected from a population with a mean of 80. Treatment is administered to the sample, and after treatment, the mean is found to be 86. So it's higher, but we don't know if it's statistically significant. We do know also that there's a standard deviation of 8. And we're going to ask a couple of different questions. Does the sample provide sufficient evidence to conclude that the treatment has a significant effect? We're going to test with 0.05 alpha level for a two-tailed test. And then, if we need to, we'll compute Cohen's d and R squared to measure the effect size. And then we're going to do the same basic problem, but this time we're going to change our sample from 16 to 4. So we're going to have a smaller sample in C. And then in D, we're going to keep everything the same as the first try, but this time we're going to change our standard deviation to 12. So our standard deviation is going to be a little bit higher than the first time around. So let's, without further ado, get started on the first question. Is there sample evidence to conclude that 86 is significantly different than 80? On the left, we have all the data that we need. At the bottom, we're noting that it's alpha 0.05, degrees of freedom are 15. And we need to set our hypotheses and determine our critical region. So let's do that. First of all, with the hypotheses, I'm going to say that the null hypothesis is going to be that the mu is equal to 80. That means that the population mean that our sample came from is equal to 80. That's what we say. The alternative hypothesis is that the mu is not equal to 80. In other words, our sample has a population mean that's not equal to 80. All right, so we've done that. That's setting our hypotheses. Next, we're going to find our critical region. And if you will look at your t-table at alpha at 0.05 in a two-tailed test with degrees of freedom of 15, our critical boundary is going to be plus or minus 2.131. So now we're ready for the next step. I have our calculation formulas on the right for both the standard error and for the t-formula, but we need to figure out the standard error first. So what we're going to do is we're going to take the square root of the variance divided by n, but you'll notice that we were only given the standard deviation of 8, so we need to turn that into the variance. So I'm going to say for the standard error of the mean, we have the square root of 8 squared, which is 64, divided by our n of 16. So basically that means we have the square root of 4. So our standard error for this calculation is going to be 2. Now that we know our standard error, we can plug everything into the formula. I have my mean of 86 minus the population mean of 80 divided by the standard error of 2. So basically that's 6 divided by 2, which gives us a t-statistic, a calculated t-statistic of 3.00. So the question is this more extreme than our critical boundary? That will be our step 4. So as we make our decision, we can look at our calculated t of 3.00, and we know it's greater than a positive 2.131. So we know that there's less than a 5% chance that we would find our t-statistic if the null hypothesis were true. And so what we're going to do in this case is we're going to reject the null hypothesis. We reject the null hypothesis that there is no difference between our mean and the population mean. In fact, we say that there is a difference and it's not likely due to error. That is our decision, to reject the null. So what we need to do next then is calculate Cohen's d and R squared. Because it was statistically significant, we can look at Cohen's d first, and the formula for Cohen's d is the mean minus the mu divided by the standard deviation. So we had our mean of the sample of 86 minus the population mean of 80 divided by 8, which gives us 6 divided by 8, which gives us a Cohen's d of 0.75, which is a medium or a moderate effect. I'm going to go ahead and put medium here. Now we have r squared that we can also evaluate to see the magnitude of the difference, and we have t squared divided by t squared plus the degrees of freedom. Our t was 3, so this is pretty easy to figure out. The numerator is going to be 9, and the denominator is 9 plus 15, which is 24. And 24 goes into 9.375, or we can say that 37.5% of the variance can be explained by the treatment effect. And in fact, when we calculate this r squared, this is actually a larger effect size. And that is because this is sample size dependent. Remember, Cohen's d doesn't have anything to do with sample size, but r squared is sample size dependent, and we had a large effect size in this case. Let's move on now to the second example, where we're going to go from a sample size of 16 to a sample size of 4. Here's the data set up just like it was before, but this time we have an n of 4. So we're going to set up our first hypothesis, which is the null hypothesis. I'm going to say that the mean is equal to 80, just like the last time. And for the alternative hypothesis, the mean is not equal to 80. The critical region in this case for a two-tailed test at 0.05 with the degrees of freedom of 3 is 3.18. So that is going to be our critical region that we need to be greater than. Let's start with the calculations by finding the standard error. We're going to take the variance divided by n, but we only have the standard deviation, so I have to square that to find the variance. 8 times 8 is 64, divided by n, which is 4. So that gives us the square root of 16. So our standard error of the mean is going to be equal to 4. So we have more error this time around. We had less people in our sample, so as a result we have more standard error. Now we can figure out our t statistic by taking our mean of 86, subtracting the population mean of 80, and this time dividing by 4. So that gives us 6 divided by 4, which gives us a t statistic of 1.50. All right, now the next step is to make a decision. For step 4, the decision we have to make is involving comparing our calculated t of 1.50 to the critical t of positive 3.18. 1.50 is not extreme as 3.18. So in this case, we failed to reject the null hypothesis, and this is how we would write it out. We would say t, degrees of freedom 3, is equal to 1.50. And we would say in this case, our p is greater than 0.05. The probability of finding RT, if the null hypothesis is true, is greater than 0.05. There's more than a 5% chance, and therefore we fail to reject the null hypothesis. And since we fail to reject the null, we are not going to calculate Cohen's d or r squared. All right. For the last problem, we're taking the same information from the first problem, except for we're changing the standard deviation. Standard deviation in the first problem was 8, and this time we're changing the standard deviation to 12. We're making it so that there's going to be more error in this next one. I think you know what's probably going to happen, but stay tuned. Let's give it a try. So on the left, you see all the same information except for the standard deviation is changed. The first thing we need to do is set our hypotheses, and this is going to be very repetitive, but the null hypothesis is that the mean is equal to 80, and the alternative hypothesis is that the mean is not equal to 80. Easy enough. The degrees of freedom are going to be the same as the degrees of freedom for, well, all of them, but the critical region is going to be the same as the first time round because we have the same degrees of freedom of 15, and our critical region therefore is going to be plus or minus 2.131. All right, let's do some calculations. We have our formulas on the right, so let's figure out our standard error first. We have a standard deviation of 12, so the standard deviation squared is going to give us 144, divided by our n of 16. Remember, we're taking the square root of that, so the square root of 9. So our standard error in this case is going to be 3. Now that we know our standard error, we can easily do our t formula. We have our mean of 86 divided by the population mean of 80 divided by the standard error of 3. 86 minus 80 is 6 divided by 3, and that gives us a t statistic of 2. And now it's time to make the decision. So the critical t value that we determined was 2.131 plus or minus, and our calculated t was a positive 2. So we can see that our calculated t is not as extreme as the critical t. So in this case, we failed to reject the null hypothesis. This is what it would look like when we write it out. Our t, with the degrees of freedom of 15, is equal to 2.00, and our p is greater than 0.05, which means the probability of finding our t statistic, if the null hypothesis is true, is greater than 0.05. So in this case, we failed to reject the null. So let's take a look and see all of these decisions in one place. In the first scenario, we had an n of 16 and a standard deviation of 8. In this case, we rejected the null hypothesis because our calculated t of 3 was more extreme than the critical value that we set at 0.05. And so, in other words, we found statistical significance. We found that the likelihood of finding RT, if the null hypothesis is true that there's no difference between our means, is less than 5%. So it's so rare that we're going to take a leap and we're going to say, no, there is statistical significance. We're going to reject that no hypothesis, the null hypothesis. All right, in the next example, though, we went from an n of 16 to an n of 4. That was the only thing that we changed. But when we did that, our calculated t was no longer more extreme than the critical t. And in this case, we failed to reject the null hypothesis. In other words, we uphold the null hypothesis. We say that there really is no difference between the mean of our group and the mean of the population. And finally, what we did in the last configuration is the same as the first go-round, except for that we introduced more error. More standard deviation. Larger standard deviation means more error. And when we did that, we again failed to reject the null hypothesis. Our calculated t of 2 was not extreme in this case, and the change is in this error. So as a reminder, those two things, I want to drive this home, is that sample size, as sample size increases, your chance of rejecting the null hypothesis increases. And as standard error increases, your chance of rejecting the null decreases. So in other words, what we really want when we're doing our studies is we want to have a large sample size, and we want it that there's not a large standard deviation in our sample. So we go for larger n's and smaller error. That's what we want. All right, I hope this is helpful. And if you have questions, you know where to find us at the Hallway Conversations Forum. Hope to see you there.